Well, hello and welcome, everyone. My name is Bob Ledoux, and I'm a program director here at ARPA-E, and I'm joined by my colleague, Dr. Julia Greenwald, who is a fellow at ARPA-E. Now, just before we begin, just a couple of housekeeping notes. We will begin this presentation with a 15-minute presentation by Julia and myself, and that'll be followed by a 15-minute question and answer period right after that. We will please put your questions in the Q&A box, which should appear on the bottom right hand of your screen. Or if you don't see it in the ellipse down there, if you pop into that, it should bring it up. And if you have any technical difficulties, please leave them in the chat post, and you'll hopefully get a quick response. So what we would like to discuss today is to explore the critical need for quantitative monitoring of hydrogen emissions. And this is spurred by the expected rapid expansion in the hydrogen infrastructure. Now, our focus here is on the quantitative measurement of hydrogen emissions to ensure that hydrogen serves as a key component in mitigating climate change impacts. And what we will be proposing here is a systems level approach of sensors and modeling combined to address this goal over a wide variety of use cases. Now, the production of hydrogen is projected to increase by up to 5-fold by 2050. And this burgeoning hydrogen economy is fueled by significant investments, both private and government, worldwide. And it will necessitate a vast deployment of new and potentially different production, storage, and distribution infrastructure. And the accurate and economical systems to quantify hydrogen emissions must be made available over a wide use, many of all those use cases. And we believe this will be vital to this rapid deployment. Now, why do we need technology to quantify hydrogen emissions? And in fact, do we need new ones? One of the main reasons for this is to proactively mitigate potentially negative climate impacts of the hydrogen economy. And we hope further that we can minimize product loss and support growth of this nascent industry. Now, there are obviously good practices here already with hydrogen, but with this rapid deployment over many use cases, it's really very important as this build-out takes place to accurately quantify what those emissions are. And furthermore, without a large body of existing emissions data, it's crucial that the hydrogen, as this is rolled out, that we measure the hydrogen very quantitatively. And we propose to do this in an area that encompasses most use cases, which is 100 meters by 100 meters for this. And now I'd like to turn over the discussion to Julia, who will talk about the impact of hydrogen emissions. Julia?
Thanks, Bob. So as Bob mentioned, our production of hydrogen is expected to increase 5-fold over the next 25 years, reaching 500 megatons per year by 2050. This will likely increase hydrogen emissions to the atmosphere. By how much, we don't know. But we can do a back of the envelope calculation and first say perhaps 10% of what's produced will be emitted. This may seem like a lot, but given that in the delivery of liquid hydrogen, more than 20% is routinely lost to the atmosphere due to boil-off, 10% averaging across all use cases seems reasonable. So of the 10% that's emitted, 20% is likely to persist in the atmosphere, while the rest is likely to be removed via biological soil uptake. So what are the impacts of adding 10 megatons of hydrogen per year to the atmosphere? Well, if we have really concentrated leaks that reach the ppm level, this can pose a significant fire hazard, but luckily we've developed a variety of technologies to detect leaks that are a safety risk. From a financial perspective, losing 50 megatons of hydrogen per year can be quite significant. Depending on the price of hydrogen, could be as much as $50 to $250 billion per year in losses. And then that small amount that persists in the atmosphere can have negative climate consequences and lead to warming, even at low concentrations like the ppb level. Next slide, please. So hydrogen is not a direct greenhouse gas. It's an indirect greenhouse gas because it has the potential to extend the life of other greenhouse gases in the atmosphere, like methane. Hydrogen has a global concentration of roughly 530 parts per billion versus methane's nearly 2,000. But both of these gases are removed from the troposphere via reaction with hydroxyl radicals, shown in orange here. And if we increase the concentration of hydrogen in the atmosphere and this hydrogen hydroxyl reaction takes place faster, then hydrogen can compete with methane for the availability of hydroxyl radicals, and this can inadvertently lead to extending the lifetime of methane. There's a lot of variables that go into this and other reactions that can be at play, but the global warming potential of hydrogen over a 20-year period has been estimated at roughly 40, which is half that of methane's global warming potential, which is 80 over the same time period, but not insignificant. Next slide. So these two factors, both the economic impact and the potential for negative climate impact via indirect greenhouse gas emissions, really drive the need for systems-level quantification of hydrogen emissions. And we're looking for technologies that can cover all of the most important use cases, ranging from exploration, production, and transportation to storage. By exploration, we're including things like identification of geologic hydrogen resources. Production, therefore, could be wellheads or electrolyzer facilities or any other type of hydrogen production. Transportation includes trucking as well as pipelines. We have thousands of miles of pipelines in this country that currently are used for natural gas, but may be used for hydrogen in the future, and then storage wherever that may occur. As a quantification target, we're interested in identifying leaks or emissions that are of 10 kilograms per hour or greater. And this number comes from looking at current EPA regulations of methane. The EPA requires a limit of detection for continuous monitoring of 0.4 kilograms per hour. And if we scale this roughly by the lesser climate impact of hydrogen and the fact that this is a nascent industry, we think shooting for 20 times EPA limits on methane, so 10 kilograms per hour for hydrogen, is appropriate. And notably, this size leak or emission can really have a negative financial impact, resulting again in $100,000 to $500,000 per year in losses, depending on the cost of hydrogen. So now Bob will tell you again about different technologies we can use and why it's hard to measure hydrogen.
Thanks, Julia. Okay, so why is quantifying emissions harder for hydrogen than, say, methane? Well, first of all, it is a very small molecule. And that, because of its very small size, it can cause leaks via embrittlement of many common materials and metals. Further, because it is a small molecule, that even customary implements such as flanges and pipes can also diffusively leak due to this being such a small molecule. So unlike maybe methane emissions and so on, we may be really dealing with a large area of diffuse emissions. And so this may make the quantification much more difficult. Further, hydrogen is not IR active. It is not a primary greenhouse gas, and therefore it does not absorb IR, infrared radiation, efficiently. This leads, therefore, to the fact that if we would like to do standoff detection, we are faced with trying to excite other modes. And these other modes can be, for example, Raman scattering. But these have much smaller cross sections than the IR absorption. Can we make up this? Can we make up for this very small cross section? Well, below you see the formula for scattered radiation from excitations of, say, a hydrogen molecule. The first term is the power term of the excitation, say a laser. But again, it's very difficult to conceive of going many orders of magnitude higher in power, if for no other reason, for safety reasons. The next term is the cross section, which is determined by the physical process. That's followed by the density, say, of hydrogen, as well as a packed length and measuring tube. Once again, that's what we're trying to measure. And the last two terms are the detector efficiency, the intrinsic detector efficiency, which again, they're pretty close to one, so there's not much margin there in the collection sorting. So the upshot of all this, unless some of you out there can come up with a very new ingenious way of doing standoff detection, there's probably this tool which is available in methane may not be available for the detection of hydrogen. So what we are proposing here, let me see if I can get up the laser pointer. What we are proposing here is a systems approach to the quantification. And this starts with, as I go on the upper left-hand side, this starts with the sensor modalities. Now, there have been many technologies, and there's a lot of current work on advancing hydrogen sensor technologies. And these include many that are listed there, from catalytic, optical, electrochemical, and so on. It should be pointed out that many of these have been developed primarily for safety considerations, and their sensitivity is much well above the sensitivity we need here. What are we talking about in terms of concentrations above ambient? We're talking about levels of probably tens of parts per billion. And so once again, these are very, very lower sensitivities than many of the existing technologies. Now, further, if we have fixed sensors, we must place them, as you see to the diagram to the right. It would be obviously advantageous to have many of them, but now there becomes a cost consideration. We may want to place them at different altitudes. We could move them around. We can either have aerial support for this or ground movement. But the main point here is that with a finite number of sensors, we have only partial sampling of this 100-meter by 100-meter area. So very important to this quantification, therefore, is an emissions model. And what that does is take all the information available, not just the sensor data, which we just discussed, but also ancillary data, such as weather data, the wind speed, direction, temperature, moisture, and so on, all contribute to the diffusion and the movement of hydrogen in this area. We also need site data, buildings, topography. These can all influence how the hydrogen can actually move in this area. And then finally, of course, before we go into the full predictive model, we need some sort of transport models for how at any given point the hydrogen will actually diffuse and be transported throughout this area. All of that must go into a predictive model, which takes all that data and essentially inverts it to predict and quantify the total amount of hydrogen in that area. This is obviously a very sophisticated process. And not only do we want to know what the actual total amount of hydrogen is, but it's also very important that we localize any significant leaks in that area. So this is a system level approach that we are proposing here, which is that it's not one or the other, but both of them together are required to really achieve the quantification we desire. In the bottom part of this figure, if we do come up with novel technologies, innovative technologies to do standoff, then I think we have some advantages there, as we do in other greenhouse gas detection, where we have much higher spatial segmentation. We obviously can get the path integral of it, and maybe we can sample it over higher temporal speeds. But nonetheless, it will still require a comprehensive predictive model to obtain the quantitative measure of hydrogen. So, putting all this together, we would like to propose some possible metrics for hydrogen quantification. We've been discussing already what emission rates are of interest to us, and that is 10 kilograms per hour as a minimum rate. We would do this across 100 meters by 100 meters, which we believe covers many use cases. And we would like to achieve an accuracy of plus or minus 20% within a 24-hour period under variable environmental conditions. We should alarm automatically for any leak or any total emission above 10 kilograms per hour. And we would like to achieve a 90% detection probability with 1% false alarms. And we'd very much like to see a receiver operator characteristic curve for that. For an individual leak of the order of 10 kilograms per hour, we would like that to be localized to plus or minus 10 meters. And for the cost, we hope that this can be done for a cost of approximately $10,000, whether that's continuous measurement, or an individual, as we said, 24-hour survey. So those are the overall metrics that we are proposing for this very ambitious systems level approach to hydrogen quantification. So to summarize, what is success in this for such a program? Well, we've already talked about the scope. The scope is really concentrated and centered on proactive mitigation of potentially negative climate impacts due to the growing hydrogen economy. We also want to ensure that there's minimal product loss in this nascent industry, and then we can also build up on best practices to reduce this. And we would like to do this over a large area, which encompasses most of the important use cases. We described everything from production all the way to end users. And the technical objectives, I won't repeat, we just went over, but we are looking for quantification of leaks of the order 10 kilograms per hour in the 100 meters by 100 meters. So with that, we have finished our presentation and we are open to questions and answers. Thank you for your attention.
All right, Bob, the first question is, how can I find out more if a FOA is released? And I think we could just say follow us on LinkedIn and subscribe to the newsletter and keep in touch.
Exactly. Yeah, this is in itself not a funding opportunity or a solicitation, but that would be the place to find any news for this or any other funding opportunity.
The next question is, can you say more about the cost metric of $10,000? Is that per day or per year?
That is for a one complete survey for the whole 100 meter by 100 meter region. So at this point, we appreciate your feedback. We are not determining whether it is a continuous measurement over a year per se, or just a single survey. So we're leaving that open at the moment.
The next question is, what approaches do you think are most suitable for monitoring leaks or emissions from pipelines? We have over 1,600 miles today of pure hydrogen pipelines, but perhaps many more are planned.
Exactly. Well, you know what we're proposing as an area to be measured. Now, we understand that a pipeline is very different sort of topology than that. We would hope that the technologies developed here, along with the modeling, both may be adapted, may have to be adapted for that. But I think the combination of the system approach of sensors and the modeling would still be applicable there, although in principle could be modified for that use case. That's a good question.
Okay, the next is, you mentioned the interest in mobile and have presented that in the context of drones or aircraft. There are pros and cons, but would you also consider the use of automobiles for mobile sampling, given that automobiles require less personnel than drones, for example?
Oh, I think that, well, that's a great question. No, we're not being prescriptive. That was just trying to give examples. Really, if you can do it within the proposed metrics, it can be done by an automobile. I don't see any problem with that at all, as long as that measurement takes place within a day, as we propose here, and it is comprehensive enough to fit into a model to provide the quantification metrics, then sure.
Okay, next question is, the accuracy measurement of 20% is noted. What is expected in terms of precision, in terms of 1 sigma factor uncertainty? Would 2x, 3x, or 5x factor uncertainty in the measured leak rate be deemed acceptable?
So that's a great question. I think for now, the global metric of plus or minus 20% as a goal for a one-time measurement, I think we can leave it there with some ambiguity as you describe. What we would probably ask in that case is to describe, in a certain sense, as you said, the probability distribution of obtaining measurements off of that central 20 plus or minus 20%. So I think that we would ask anybody that proposes to explain exactly what the distribution looks like. that they measure would be even better.
Okay. The next one is, what measurement time do you have in mind regarding the tens of ppb detection precision?
So that's one is where we're doing a systems approach. So we have not individually specified what the sensor time sampling is. We've done it in terms of the systems level approach and the total time to do the survey. So we bounded that only, and I think it is open to your particular solution, whether the sample time could be longer, in which case, but you would have to do all the measurements we're proposing in a day and do the full inverse modeling within that time period with the measurements. So we're not directly specifying that.
Okay. Next is, can you explain more about the model? Will you take data given by some sensors and then input that into a model? If so, how would that enhance the sensitivity towards detection of hydrogen gas?
Well, again, we're not going to prescribe how that works. What we're saying is that the system clearly needs hydrogen sensors, and the inverse model must contain enough information with a high fidelity inversion to give you the quantification limits we like. So there are a number of approaches devoted to this, but that's why we want a system approach, because there's many ways of accomplishing that. Sometimes you may have a plethora of sensor data, which makes the inversion in some sense a little easier. Maybe you have sometimes a more sensitive detector, which allows you to do maybe sample on the perimeter where the mixing is better. We're not going to define that, but what we do ask for is a systems approach. So the model and the sensors must be combined into one system to yield the desired metrics.
Okay. Next would be, are there any plans for all weather requirements or high availability sampling?
Yeah. So the answer is, again, is the metrics we propose don't specify those exactly. We use variable weather conditions. I think that would be interpreted that nothing extraordinary, but typical weather for a region would be in scope. So I think that, what was the latter part of the question, Julia?
It just says / high availability sampling.
Yeah, I'm not exactly sure what that means. Again, you have, I guess in a certain sense, you have the choice of date potentially when you do that measurement. And so it must be done within a day. But I think that, it's really up to you to explain exactly under what conditions you can do it. And as long as you're within those specs, I think it would be considered.
All right, the next question is, you mentioned the expectation to detect hydrogen concentrations around 10 parts per billion. Typical concentrations of methane emissions at 10 kilograms per hour at 100-meter facilities are closer to 10 ppm. Why do you expect so much lower concentrations for hydrogen?
Yeah, well, it depends on the mixing model. It depends on the number of senses you have. And again, that is in some models that we have seen, that's kind of the sensitivity you need at certain parts in that 100-meter by 100-meter. But again, we're not going to be prescriptive here. I would think that if you can do the sensing and the modeling in such a way, demonstrably, with whatever sensitivity measurements that you provide, then there is no concentration sensitivity limit that we are imposing on the senses as we presently conceive this.
All right. Wow, there's a lot of questions. This is great to see.
Well, Julia, if you have any answers to these, just butt in and let me know.
Well, okay, so the next one is, if the cost target is $10,000 for a 100-meter by 100-meter area, do you envision 10,000 for every 100 meters of hydrogen pipeline? Won't you need different metrics depending on the application?
Well, again, this pipeline question has come up before. The 100-meter by 100-meter is what we're putting the specifications in as we presently conceive it. We appreciate your feedback. With a pipeline, As we presently formulate the metrics, you would have to show that you hit the metric we propose. Whether that's applicable to a pipeline or not is something which we would probably not directly call out. If you would like to make the case that you could do the measure in 100 meter and it is applicable to a pipeline, I'd assume that's a plus. But the metric as a whole would be in that 100 meter by 100 meter alone. Do you have anything to add to that, Julia?
No, I mean, I think that this is sort of a nascent field, and so what actual deployment looks like in the future might need to be adjusted, but these are initial thoughts.
Yeah.
Okay, the next one. Okay, oh, there's a clarification regarding high availability. It says you would need to accommodate 95 calendar days in a year rather than only on dry, clear days, etc. So I think, yeah, the availability is going back to this weather question.
Oh, I see. I see. Let us think about that. I think if there's just, if measurement can be done under, quote, reasonable conditions, then the availability we would not specify. And what do you think, Julie? I think in this case is, let's see the measurement on some varied weather conditions, and then how it's actually deployed and what the monitoring scheduling would be at present. I think we view that as unspecified.
All right. And then another, just getting through, there's so many, it's great to see the engagement. Can the sensors be co-located with the likely leak sites? At the beginning of the presentation, I was under the impression you were only interested in remote or standoff monitoring.
No, we are definitely not only interested in a remote standoff. And I guess in a certain sense, I try to make a point that for hydrogen, without some real innovation, that in fact may be extremely difficult. So no, I think definitely fixed sensors placed throughout that area are certainly in scope, as long as the combination of the sensors and the modeling and the cost metric are met.
Okay, and then I think maybe our last question is, where did the 10 kilograms per hour come from? Many facilities, such as current fueling facilities, don't have large hydrogen storage, less than 100 kilograms. This rate would deplete the capacity in 10 hours. Should this leak rate be scaled by facility capacity? Currently, a large facility is 600 kilograms or so.
So I'll let you give the very first part of that, Julie, of why we chose 10 kilograms, because you did it beautifully in your presentations. And then I maybe can comment on, even though a small facility may not have that much, again, we're trying to cover a lot of use cases. If you can do it in this area, then I believe that you could, the industry itself could scale it down to the appropriate size. But we're shooting for an ARPA-E hard problem, I think. And maybe you want to say a few words on where 10 kilograms per hour came from.
Yeah, I would just say that we were thinking about it in the context of current methane regulations, where there's this proposed limit of detection that is a third of whatever, the allowed emission rate is. And we were trying to scale that by the potential emissions intensity of hydrogen. And so it has a lower greenhouse gas impact. So you could have a larger emission rate, and that's where it came from.
Yeah, so we completely understand the scaling argument, but for the purposes of what we're proposed here, we really want to cover as many use cases as possible, which includes very large production and potentially storage and distribution facilities. So we hope to cover that, which we think is the one that probably have very little existing data on. And so it's important to capture that. And to capture that, we need to be able to quantify it. So thanks for all the fantastic questions and the engagement. You know where to reach us, and we look for further engagement on this. I think from this interest, it shows that just how important this problem is, and we look forward to working together, hopefully in the future. So thank you.
And so sorry we weren't able to get to all of the questions.
Yeah.
It's 2:00, and we thank you so much for your participation.
Thanks, everyone.